Hello everybody, it's Mrs. Walsh, and sorry, I think that hopefully this mic sounds better. This is our last video lesson of the unit, and it's on area and volume of similar solids. So we're going to find and use scale factors of similar solids, and we're going to use similar solids to solve real life problems. Okay, so if we have two solids that have equal ratios of corresponding linear measures, such as heights or radii, we call them similar solids. And the common ratio that allows us to correspond their sides is called the scale factor of one solid to the other solid. So any two cubes, of course, are similar, because in a cube, if it's truly a cube, this side's congruent to this side, which is congruent to this side. And if the next one's a cube, then whatever the scale factor is that got from one side to the other is going to be the same. The same is true for any two spheres, because a sphere is the set of all points equidistant from a single point in space, and you'll always be able to come up with a similar factor that you go from one to the other on. But in shapes that aren't like that aren't cubes and aren't spheres where they're all regular sides and everything is the same, there can be non-similar solids. So this is an example here of two non-similar cylinders, because it's clear that the ratio to go from here to here, those are not similar figures. So to talk about this in more detail with actual numbers, if you look at these two rectangular prisms, this is a scale factor of 2, and this is a scale factor of 2, but this is only a scale factor of 1. So no, these are not similar. Whereas you look at this one, it's a scale factor of 2, it's a scale factor of 2, and it's a scale factor of 2. So those are similar. Yes, they are similar solids. So if you want to look at it as ratios, you can say that in the case of the first one, it was a 3 to 6 and a 1 to 2, which gives us 1 to 2. It was a 2 to 4, which is a 1 to 2 ratio. And this was 2 to 2, which is 1 to 1. So those ratios are not all the same. In the case of the second example, 3 to 6 gives you a 1 to 2, 2 to 4 gives you a 1 to 2, and 2 to 4 is 1 to 2. So they are similar solids. And when we look at two similar prisms, we can find out some interesting relationships. So here's another case where our ratio is 1 to 2, or it's a scale factor of 2. So this is a 1 to 2 ratio, 1 to 2 ratio, 1 to 2 ratio. And if I calculate, volume's easier to start with, if I calculate the volume of this, it's 2 times 1 times 3, which is 6. And if I calculate the volume of this prism, it's 4 times 2 times 6, which is 48. And I noticed something interesting, that's a 1 to 8, or a scale factor of 8. And if I look at the surface area of this, it'd be 2 plus 2 plus 3 plus 3 plus 6 plus 6, which gives me 22. And this one, it would be 8 plus 8 plus 12 plus 12 plus 24 plus 24, which would give me 88. And you can see that that's a 1 to 4, or a times 4 kind of ratio. So this kind of ratio didn't just happen with these two prisms, it always happens. And it leads us to a theorem that basically states if I have two similar solids and the scale factor between those solids is A to B, then the ratio of their areas, and when I say area, that could mean their surface areas, their lateral areas, any sort of area measure, is going to be a ratio of A squared to B squared. And if I look at the ratio of their volumes, it will be A cubed to B cubed. So this is interesting. If you think about why, I think it's very easy to see if you think of a rectangular prism and you look at volume, right? So if I had a rectangular prism with a length and a width and a height, for volume it's LWH. And let's say I was going to use a scale factor of 2. And I was going to change each of these. So now this is 2L and this is 2W and this is 2h. I made each dimension twice as long. Well, I could rewrite this to be 2 times 2 times 2 times LWH, which is really 8LWH. So you can see what happened is if my ratio was 1 to 2, which is what I did here, then my scale factor for volume is going to be 1 cubed to 2 cubed, which is 1 to 8. And it's logical to see why that happened, because I took my scale factor and it's happening 3 times, because volume is a length times width times height kind of measure. It's a 3-dimensional measure, so it's logical that that would be the case. In area measurements, where for a prism my surface area is 2 times LW plus 2WH plus 2HW. Once again, if I doubled each of these, it'd be 2 times 2L, 2W, plus 2 times 2W, 2H, plus 2 times 2, oh, I did that wrong. That shouldn't be HW, that should be LH. And so 2 times LH times 2L times 2H. You can see if I simplify each of those, I now have 2LW and a 4 that I can pull out because of the 2 times 2. Plus 4 times 2WH plus 4 times 2LH, and you can see that my surface area is 4 times as much. And that makes sense because when you're doing an area measurement, it's a 2-dimensional measurement. So the impact it has is that scale factor, which in this case was 2, twice, which gives you 4. So to me, this is a logical theorem. All right, so if we're going to take a look at scale factor of similar solids, I'm telling you these prisms are similar, and they have a scale factor of 1 to 3. Hold on, I need to move this in. I don't know why that just expanded. Okay, sorry, fixed it. So anyway, if I look at this and I'm being told that the surface area and volume of a given prism G, if I need to find the surface area and volume of G, given that this one, F, has a surface area of 24 square feet and a volume of 7 cubic feet. Let's see what we can do with that. Well, I'm going to use the theorem to set up the proportions. I know if they're similar that the surface area of F to the surface area of G has an A squared to B squared ratio, and I know that the volume of F to the volume of G has an A cubed to B cubed ratio. So I do know the surface area is 24, and I don't know the surface area of G. But I do know, in this case, if you look back here, that I've got a 1 to 3 ratio. So I can put my 1 to 3 in for A to B, and that becomes a 1 to 9 ratio. And if I cross multiply, I will see that the surface area of G would be 216. And for volume, that same 1 to 3 ratio, which in this case gives me a 1 to 27 when I cube it, and I do 7 times 27, and I would get the volume of G to be 189. So the surface area of prism G is 216 square feet, and the volume is 189 cubic feet. So it's easy to use those ratios to find that information. I could also easily check my work if I go back in and substitute in what I found. I substitute in the 216 and substitute in the 189. I better get these ratios, and I did. All right, and so if I'm given 2 volumes and I need to know what the scale factor is between these 2 cubes, I just need to look at the ratio of the 2 volumes. So I know A cubed over B cubed is 512 over 1728. And I would write that ratio, and then I take a look and say, well, but I want to take the cube root of that, and I want to take the cube root of that, because I want to know what the ratio is, right? So, I'm sorry, I already took the cube root down there. So I want to know the ratio, and if I put that in my calculator, I would find that the cube root of 512 is 8, and the cube root of 1728 is 12. And I wouldn't leave the ratio as that, of course. I would make sure I simplified it, but this is a 2 to 3 ratio between these cubes. All right. Now, I think you're going to have trouble seeing this. I'm going to write this right here. I think it's cut off for you. but let me show you this. Okay, in meteorology, the lift power of a weather balloon is the amount of weight the balloon can lift. If I find the missing measures in the, I'm going to find the missing measures in the table, given that the ratio of lift powers, this ratio of this lift power to this lift power, is equal to the ratio of the volumes of the balloons. So to find this, I've got to find the volume of the smaller balloon, and I know if its diameter is 4, that it is 8, then its radius is 4. So let me first find the volume of this balloon. I would use my formula 4/3 pi r cubed. And I would substitute in 4, and I would find that this one is 85.3 pi feet cubed. And when I substitute that in, and I now know also that if this is 17, the scale factor of the two balloons, if I look at this, is a 1:2 scale factor. So the ratio of the volumes, it's a cubed over b cubed. So it's 1 cubed over 2 cubed, which would be a 1:8 kind of ratio. So to find the volume of the larger balloon, I'm going to multiply this volume by 8, and I'll get 682. And then to find the ratio of the lift powers, it's 1:8 as well, right? So to find the lift power of the larger balloon, I just multiply the lift power of the smaller balloon by 8. All right, and then finally, comparing similar solids. If I have swimming pools, two swimming pools, I'm telling you that they're similar, so their shapes are similar, and it's a scale factor of, I guess it's going to go 3 to 4. And I tell you that the amount of chlorine mixture to be added is proportional to the volume of water in the pool. So if 2 cups of chlorine are needed for the smaller pool, how many cups of chlorine are needed for the larger pool? So I would use the scale factor, and the ratio of the volume of the smaller pool to the volume of the larger pool is as follows. Once again, a cubed to b cubed, if it was a 3 to 4 ratio, that makes it a 27 to 64 ratio that for the purposes of trying to measure cups, I'm going to simplify to a 1 to 2.4 ratio. So if it's 1 to 2.4 and I'm using 2 cups in the smaller one, I just multiply 2 by 2.4 and I get 4.8, and that's how much I would need to add to that pool. All right, so that's it for this. Be prepared for to come in tomorrow. We'll be doing some work on this and some review. So see you guys tomorrow.